Okay, right, sometimes these diagrams can start to get a little bit tricky. Okay, so let's have a look at this. A ticket is selected at random from each of the boxes. Show a tree diagram to display the possible outcomes. So we can do box A, just change colour. Box A, we can get red, blue, or green. So sometimes you need to have more trees, okay? And you'll see that it's going to get quite messy. Okay, so probably getting red is, how many are there? 1, 2, 3, 4, 5, 6, 7. 3 out of 7, 2 out of 7, 2 out of 7. From box B, I can also get red, blue, green, and then I need to branch off from each of these as well. And you can see how it can cause a bit of a headache, which is why you need to make lots and lots of space and do this beautifully and clearly. Okay? Notice that what you take from box B is independent of what you take from box A, so that helps save me some time. Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 2 of which are red. So 2 out of 9, blue is 3 out of 9, and green 4 out of 9. They're independent, so I can just copy these down. 2 out of 9, 3 out of 9, 4 out of 9, 2 out of 9, 3 out of 9, 4 out of 9. Don't be lazy, list your outcomes. So I can get red and red, red and blue, red and green, blue and red, blue and blue, blue and green, green and red, green and blue, green and green. And now probabilities, okay, no lazy tree diagrams. Is going to be 6 over 9 times 7 is 63. So I know the denominator is always going to be 63, that's why I don't simplify things. So 9 over 63, that's how I'm able to do things really quickly. Okay, 4 over 63, 6 over 63, 8 over 63, 4 over 63, 6 over 63, 8 over 63. Now I've done a non-lazy tree diagram, I can now do part B and actually answer the questions. So find the probability of obtaining a blue and a green ticket. So probability of blue and green in any order is, let's just use a different colour, blue and green in any order. So that would be blue and green or green and blue. So it's that or that, so add them together, it will be 14 over 63. Okay? 2 tickets of the same colour. So probability, same colour, will be equal to, that's the same colour, that's the same colour, and that's the same colour. So it's this plus this plus this, so 6 plus 6 plus 8, 20 over 63. 2 tickets of the same, so exactly 1 pink ticket, I think I read that as red. So I'm saying probability of exactly 1 red. Exactly 1 red. Well, that's let's just use a different colour so I don't confuse myself. That's exactly 1 red. That's exactly 1 red. That's exactly 1 red. And that's exactly 1 red. So let's add them together. It's 9 plus 12 is 21, plus 4 is 25, plus 4 is 29 over 63. So once you've got a really nice non-lazy tree diagram, it becomes very easy to answer associated questions with it. Okay? What about this one? A container has 4 purple, 3 blue, and 1 gold ticket. Three tickets are selected without replacement. So I'm not putting the ticket back, and that means these are dependent on each other, because what I pick first is going to affect the chances of what I pick next. And we're doing, wow, this is going to be a nightmare, this one. Let's just do it very, very carefully. What we're saying is we're picking 3 tickets, so we can pick ticket 1. And it can be purple, blue or gold. Purple, blue or gold. The second ticket, well, let's just think about this carefully. If the first ticket is purple, I can still pick purple, blue or gold. If the first ticket I get is blue, I can also get purple, blue or gold. But notice there's only 1 gold ticket. So if I pick gold ticket first, I can only actually pick purple or blue, because there will be no gold ticket left because I'm not putting them back. And now, God, this is a nightmare because I've also got ticket 3. Well, I've done 2 purples, so I can still get purple, blue or gold, purple, blue or gold. You can see why this is a nightmare. I've basically made a right mess of this because I haven't left myself enough space. Notice that if I took gold the second time, there's no more gold left, so I can do purple or blue. Okay? Hopefully you understand where I'm going with this. I'm not going to actually answer the whole question because I just don't have enough space. You can do it yourself and see how you go. You'll need a whole sheet of paper, 1 big sheet of paper to do this. Let's just have a look at the probabilities though, so we understand what's happening. Well, if I take a purple the first time, that's 4 out of 8. To then take a purple the next time, I would only have 3 purples left because I already took a purple out of 7 in total. I still have 3 blues and the 1 gold. For the third ticket, I've now taken 2 purples out. So I've only got 2 purples left out of 6 tickets in total. I've still got 3 blues and I've still got the 1 gold left. Okay, now this time round I've taken purple and then a blue. So there's 1 less purple and 1 less blue. So if there's 1 less purple, I've got 3 out, let's change the colour, 3 out of 6, you see why I need the space. I've got 1 less blue, so there's only 2 blues left, and 1 gold left. Now this next one I'm saying I've taken a purple and a gold, so I've got 1 less purple, so that's going to become 3 out of 6, but I've got the same amount of blues, 3 out of 6, and there is no gold left to speak of. So I would need to do that for each of the bits down here as well, and then don't be lazy, do my outcomes, do my probabilities. I simply don't have enough space on my tiny little PPT to do this properly, so I'm not going to. You can work it through yourself, and then once you've done a non-lazy tree diagram, you should be able to answer these questions as well. Let me know if you don't understand, okay? Let's go to one where it's a little bit more doable. Okay, so here we've got a hat contains 12 tickets with the numbers 1 to 12 printed on them. If 2 tickets are drawn from the hat without replacement, find the probability they are both prime numbers. Now, you can imagine this, what we've got is a bag or a hat or whatever with tickets in there. 1, 2, 3, 4, 5, 6, so on, all the way up to 12. Now, you could be really, really silly about this, and you could say, well, ticket 1 can be a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, 11, or a 12. This is stupid, isn't it? Look at it. What an absolute mess. Okay? That's going to be a nightmare. You need to make your tree diagram useful to the problem that you're going to solve. And actually, my question is all about prime numbers. I want to know whether I'm going to get 2 prime numbers. So instead of saying my outcomes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I'm going to say my outcomes are it's a prime number or it's not a prime number. You need to make the tree diagram useful to you so that you'd have to put the minimum effort into solving the problem. And ticket 2 can also be a prime number or not a prime number. Okay, so what are the prime numbers? It's 2, 3, 5, 7 and 11 below 12. So that's 1, 2, 3, 4, 5 out of 12 and 7 out of 12 are not prime numbers. Now, what you've got to do is realise, though, that these are conditional, because if I took a prime number out, there's going to be one less prime number to pick from. So it's going to be 4 out of 11 if I picked a prime number, and then there'll still be the 7 non-prime numbers that I didn't pick. However, if first time I didn't pick a prime number, then I've still got 5 prime numbers left, and only 6 non-prime numbers left. Okay, so make the tree diagram useful to you. Now we need to do outcomes and then associated probabilities. So my outcomes are a prime number and a prime number and not a prime number, not a prime number and a prime number, not a prime number and not a prime number. Associated probabilities are 5 over 12 times 4 over 11, which is 20 over 132. Okay, so that will be 35 over 132, 35 over 132, and 42 over 132. Find the probability they are both prime numbers, prime and prime. There's my answer, 20 over 32. So the probability of both being prime numbers is 20 over 132. Okay.